Right. So now from this point onward, I will be taking the lectures from Miss Aisha. Right. So as you know, this subject applied thermodynamics is a continuation of what you have learned from the second year. It's a subject called engineering thermodynamics. Right. So so basically what you have discussed so far is about gas power cycles, right? So this point onward I will be discussing about vapor power cycles, and then goes to refrigeration cycles, right? So as I said so far, now let me draw what you have discussed so far is, right? So right, so basically we have in here heat engines, right? Engines, and then we have heat pumps, right? So on the heat engine we have gas power cycle and we have vapor power cycles, right? So on the gas power cycle you may have discussed about the Otto cycle and the diesel, and then Brayton cycle, right? Now I'm sure that in the second year in engineering thermodynamics you already we already discussed about Otto and Otto cycle and the diesel cycle, right? Because I'm the one who conduct the lecture, so therefore I know we already discussed about this one, right? In this module also you may have discussed about those things, right? But of course as I said, we have a kind of overlap between these two subjects, but basically this is a continuation of what we have learned in the second year, right? So therefore you have gone up to Brayton cycle, right? So same thing goes for vapor power cycle as well, right? So we start with the Carnot, then to Rankine, and then we going to extend the Rankine cycle to reheat cycle and regenerative cycles, right? Then so we will be basically discussing more about the Rankine cycle and the reheat and regenerative version of that one, right? So so the today's session is actually to recall what we have done already, right? Basically discuss about the Carnot and Rankine cycles. Then we will, after that one, we will look into the more details on the reheat and regenerative cycles. Then under the heat pumps, you already worked with refrigeration cycle, right? Refrigeration cycle. Then under there we have absorption cycle, something called absorption cycle. So we will be discussing about those two as well, right? So that's the kind of overview, right? But today's session is actually on pure substance. In this case also I already covered this one in the second year, but let me like quickly go through it and try to memorize the thing, and that will be help to go through the session, right, very effectively. So so pure substance is a mixed chemical composition throughout if you have mixed chemical composition throughout the volume, then we call it as a pure substance, right? For example, water, nitrogen, helium, carbon dioxide are pure substance, right? So I have some of the compartment here. So one is filled with N2. So what we can check, how we can check whether this is a pure substance or not is, we get a sample in there, somewhere in here, right? Then we analyze the composition. What we get is 100% N2, right? Okay, then again we get a sample somewhere random places somewhere else, then analyze it again, it is N2, 100% N2, then we can say it is a pure substance. Then air, of course air is a mixture, right? So air we have oxygen, nitrogen, argon, likewise different gases, but the mixture is homogeneous. That means we have the same composition, right? Same mixture percentages throughout the samples. Therefore we can say air also is a pure substance, right? N2 is a pure substance, air is a pure substance, right? Now in here we have liquid water, and we have here vapor water, right? So whether this is a pure substance or not, of course this is a pure substance, because you get a sample here, analyze it, you get 100% water, right? And if you get a sample here, again we have 100% water, right? 100% water. Okay, it doesn't matter the state, right? You have the liquid state, you have the gaseous state, but what you see is 100% water, therefore this is a pure substance, right? Again we have liquid air, and of course vapor air, again this is also a pure substance, right? But if you have something like this, right, you have here water, right, water, and you have air here, right, air. Of course this air also contain H2O, right? This is 100% H2O, right? 100% H2O, but this is not 100% H2O, right? Therefore this kind of a container we can't say it is a pure substance, right? Again oil and water, we can't say it is that one as a pure substance, right? So I hope you remember this thing. Then we normally discuss about three phases. We have solid, liquid and gases. And solid, you know, we have very structured array of element, right? Then inside you can have vibration and rotation. Then the liquid state, you have group of elements. They will be moving randomly, but it is a group, right? It's a group of element or atoms connected together. Then that group moves randomly. In gaseous state, of course, we have individual atoms, so molecules, right? Then you can have random movement, vibration, rotation, and likewise, right? So basically three phases, right? Then critical temperature, right? I hope we discuss about this one. I hope you remember this one. We will come to this graph later on, right? Okay. So what is the critical temperature is, now this is a PV graph, right? And these are the temperature lines, right? Okay. Now any subject, I mean anything you can find critical temperature and critical pressure, right? So we will come to that one later on, right? Now now we're going to do a small experiment, right? So I hope you already remember this one. We did this in the experiment in engineering thermodynamic, but let me quickly go through it, right? So what you have here is a cylinder piston arrangement, and the cylinder is frictionless, right? And you don't have any heat exchange throughout the wall, right? And this piston can slide, and there's no heat loss or work loss, right? So what you have in here is H2O, right, water, and we are doing this experiment in 1 atm pressure, right? So the same time we going to draw a PV diagram for this experiment, right? Okay. So we have the pressure, we have the volume, right? So initially we apply heat, and we starting the thing is at 20 Celsius, right? So let's say this 20, right? Then what happened when we increase the heat? The temperature of this water gradually increases, right? When the temperature increases, right, therefore the volume increases. So we can say volume will be increasing, right? Therefore we can right, sorry, we are going to draw not PV, we are going to draw T and S, temperature with volume, right? Temperature with volume. So we know the temperature is increasing, and the same time V is increasing, therefore we can say like this, right? So when this come to 100 Celsius, you know that 100 Celsius the water start boiling, right? Therefore some of the water molecules escape as gas, right? Then this volume gradually increases, right? We supply heat, the volume increases, but the temperature is not, right? Whatever the heat supplied absorbed by the liquid, and some of the liquid escape, turn into gas, right? Then therefore the volume increase but the temperature is not, therefore we can observe a flat graph, right, like this flat line. Okay. then at some point we get all of these liquid become vapor, right, say at this point, right. Then if we further heat it, now you have a gas here, 100% gas, right. Now in this case you have some portion liquid, some portion gas, that we have a mixture here, right, liquid and gas mixture. Then when all the liquid become gas, you have 100% gas. After that it's expanding. When you supply the heat, you have a gas and gas expand, therefore volume increases as well as the temperature increases, right. So this is the graph for 180, right. Now if you do this experiment in elevated pressure, that means let's say 280, right, what you see is something like this, right. Okay. And if you continue to do this one, right, you will get something like this, right. Let me show you that one. So let me first discuss about these lines, right. So this is the experiment that we did in 180. So up to point 1 to 2 we normally say we have liquid, 100% liquid, therefore we say this compressed liquid, though we call subcooled liquid, right. We have subcooled liquid here, or we can say compressed liquid. From this point to this point, right, 2 to 3, we have a mixture, we call saturated mixture. So this is 100% 100 Celsius in saturated mixture. From this point on, we call this superheated vapor. What we have is superheated vapor. So somewhere in between these lines we have a mixture. We have some portion of liquid, some portion of gas. So for example, let's say at this point number 3. So this portion, what is this portion? So this portion is the gas portion. This is the gas portion and this is the liquid portion, right? If you get a point in here, what we get? We get 100% liquid. This 100% liquid. At this point we have 100% gas, right? Somewhere in here we have this amount of gas and this amount of liquid, right? Now if we continue that experiment with different temperature, different pressures, so we will get something like this, right? So there's a point where this flat region, now when we increase the pressure, what happens? This flat region reduces gradually, right? So there is a point, there's a particular temperature, particular pressure and particular volume, of course, right, where this line become a point. So that point we normally refer as the critical point, right? So beyond that point you can't convert gas into liquid. Now if we start from here, right, what that means is, if for example let's say we about this line, right, so let's say we start from this side, we come in this way, right. So what we are doing is we have some pressure, we have a certain pressure and we are reducing the volume, right. So by reducing the volume we can convert that gas. So what we have is a superheated region, that means a gas, you can convert that gas into a liquid, right. Okay. While you compressing it, right, you are reducing the volume. In that way you can compress that one into a gas into a liquid, right, gas into a liquid, right. But beyond that point, right, beyond that critical pressure, beyond that critical pressure and critical temperature, this doesn't matter how much you compress, you can't convert that gas into liquid. So that's what this critical point means, right. Beyond that point you can't convert a gas into a liquid, right. Then what we do is we join this point, right, then we make this graph, right, likewise, right. So I hope you remember these things. That's how we get our famous graph, right. Right, so these are saturated temperatures and pressures for different gases, right. Then these are some of the applications, right. So so pressure cooker, and autoclaves, right? Pressure cooker, we use in our day-to-day life. Normally pressure cooker cooks the meal, whatever vegetable or thing, in elevated temperature, right? So normally, let's say you are boiling an egg in open pit or open pot, you can boil an egg at 100 Celsius, right? But in pressure cooker, it may be 120 Celsius or somewhere elevated, right? So then autoclaves, of course, autoclaves are used in medical industry, to sterilize the things and kill the germs and so on, right? Again, this work in elevated temperatures. That means they boil the water in elevated temperatures, not at 100 Celsius, but 120, maybe 130 likewise. Okay. Again, another example is vehicle cooling system. Of course, your vehicle cooling system operate in higher pressure, not 1 atm, right? In higher pressure, and it boils the temperature not at 100 Celsius, but in elevated temperature, right? Basically, your car engine cooling system work on 120 Celsius, right? Okay, but it's still in liquid form. It's not going to boil the things, right? Because you have increased the increased pressure, and it maintaining pressure higher pressure than the ATM. Therefore, water remain its liquid form, right? It's not going to boil off, right? That's why normally people say don't open the radiator cap. So what you have is a radiator cap. Don't open the radiator cap until the engine cools down, right? You have to open the radiator cap when the engine is cooled down, right? Otherwise it will give you a high. So what you have inside the high pressure liquid, but when you open the radiator cap, what happened? The system pressure suddenly dropped. At that point, your water evaporate. I mean, water boiled off very fast, and then you can get burned, right? That's why normally people say don't open the radiator cap until the engine cools down, right? Those are some of the applications, right? Again, so we have a picture here. So I think this is something that you see normally. What I want to highlight here, you can see the white smoke in this area, but not in here. So why it is that? Because this portion is superheated, and this is saturated, right? In saturated water, you can see it white color. That's why you can see clouds in white color and the fog in white color. But if it's superheated, it's colorless, odorless, right? So you can't see any visually, you can't see that one, right? And of course, what you have inside the pot, right? So you have the water here. Water is 100 Celsius, right? And then you have saturated steam here. Then saturated, when boiling means some of the liquid turn into gas, then that vapor or the gas travels in here. Then what happened? That gas jump around and absorb more energy from these surfaces, right? Then become superheated. So what you have inside is superheated steam. So that superheated steam escape to this nozzle. That's why you see this one as a without a color, right? So after escaping, they dissipate the extra energy to atmosphere, then it becomes saturated. That's why you can see it in white color here, white smoke, but not in here. So this portion is superheated, this portion is saturated. Okay. So those are the observations, right? Okay, so I'm not going to discuss this one, right? Okay. Right, so so this is our famous graph, right? Temperature and volume, right? So we already drew this one. So we call this line as saturated liquid line. So you have the critical point here, right? From this point to all over there, we call saturated liquid line. From this point to this side was we call saturated vapor line, right? So if you mark any point in this side, we have 100% saturated vapor. In this line we have 100% saturated liquid, right? Then in here we have compressed liquid region, or we call subcooled liquid, and in here we have superheated. So these are all superheated regions. and this in the middle we have mixture, right? Saturated water and vapor region. That we have basically we have mixture there, right? We have saturated water and well as we have saturated gas, right? Okay. Then so this one is for temperature and volume, right? Then this graph we can draw it for pressure and volume, right? The same thing goes here. Now in temperature and volume we have the pressure line, right? So these are pressure line, it goes like this, P1, then P2, P, right? So this P1, P2, P2 is larger than P1. That's mean higher pressure goes in this way, right? If you draw another line like this, let's say P3, so P3 is larger than P2 and larger than P1, right? Likewise. Then same way, if we draw a pressure and volume, our temperature line goes like this, right? So this is the temperature line, and also the temperature line like this, right? Then T2 here, T1 here, the temperature increasing in this way, right? T2 larger than T1, right? If you draw another line here like this, let's say the T0 is right less than T1, less than T2, right? Okay. Increase in this direction, increase in this direction. All right. Then of course we can extend this graph, right, PV diagram and TS diagrams to solid phase as well, right? So now this one is a pressure and volume graph extended for solid phase. So we have gas, so gas, liquid and solid, all the three phases are there. And now we have two graphs for this one, because some of the substance contract during the solidification. That means the volume reduce when you transfer from liquid to solid, volume decreases, right? So this is the graph for that kind of material, right? So now if we draw a particular line, let's say we are compressing a liquid, right? So it's come there. Now we have superheated region, then we have saturated mixture region, right? Then we have liquid subcooled region, right? Then now this transition goes like this, converting liquid to solid, right? So in here you have 100% liquid, in here 100% solid, right? Because solidification. So this is solidification. From that point onward, it goes like this, right? Okay. That means when you are converting from liquid to solid, your volume decreases, right? Okay. So in here you have the solid. So you have solid and liquid and vapor, and superheated region for the vapor, right? You have the critical point here. Then in here you have solid and vapor, right? And this line we call the triple line. So what is the important is triple line is, right, if you pick any point here, right, any point here, then you will find there are solid, liquid and gas, right? All the three phases are present in this one, right? Okay, that's why we call it a triple line. Sometimes it's called triple point for some of the diagrams. For example, if we look in the P and T diagram, you will see it as a triple point, right? We call triple point. But the other graph, PV and TS diagram, we call it as a triple line because it is an actual line for PV and TS diagrams, right? Okay. Right. So and for example, let's say you are compressing in a temperature lower than this one, right? So what you see is now like this, right? You compress something like this, what happened? That means you have gas here and you are converting gas into solid, right? Gas into solid. If you convert in this region, that means you are converting gas into solid, right? That means there is no liquid region, right? So now this graph is for substance that expand when they freeze. For example, water. What happens in water is when you freeze the water, that means you are converting liquid water to ice, your volume increases, right? Volume increases. There are substances like that, right? So for that one, it goes like this. So this PV diagram, right? So what happens is when you compress it, this goes something like this way, right? And it goes this way. Then this is the solidification. Solidifications come like this. Then again the pressure increases. Right? Now you are compressing it, right? So you have temperature line here, particular temperature there, right? You are going that way, compressing it, and this goes up to here. Then volume increases when you compress it more. I mean, then what happens was the volume increases. Then it goes like this. Okay. That's how we can draw that. Right. Now we talk about this region, right? Solid and vapor, right? Now in this region, what happened? Solid become a gas. There is no liquid region, right? For example, it's dry ice, right? I hope you see the dry ice. Some of the parties and in the weddings they use dry ice to make the smoke. So basically what happens in dry ice, so you have the solid ice instantly become a gas, right? There's no liquid phase in dry ice, right? That is the because of dry ice act on this region, right? Work on this region. For the particular temperature and pressure for dry ice is comes under this region. That's why it instantly convert from solid to gas. We call sublimation. This called sublimation, right? Sublimation. Right? That means solid to vapor, converting solid from solid then to vapor. There is no liquid phase, right? Okay. Right. Then we talk about the triple line and triple point. So in the PT diagram, you will see this one as a point, right? Triple point, where the other PV and TV diagram, you will see a line, triple line, right? So why is this that? Because let me draw this one in 3D, then you will be able to understand. So these are the 3Ds. You have the pressure, you have the volume, and you have temperature, right? Now if you look from this side, now this have the triple lines. So let me try to see this one in this way. If you try to this side, what you see is this one as the temperature and this one as the volume, right? Basically TS diagram, right? So TV diagram, right? TV diagram. Then you will see this curve like this, right? So what you have T and V diagram, this curve like this, right? The normal that we the same diagram that we have discussed in earlier, right? Then if you observe the things from this side also, right? Observe from this side, you will see the PV diagram, P and V, right? What you see P and V diagram, right? Again the same graph, right? Like that. But you observed in this side, right? From this side, this way, what you see is P and T diagram, right? And this line, you have a line, but you see a dot here instead of this one because you are observing from that side, right? So this triple line become a point. That's why we call this a point, triple point. For PT diagram, it is triple point, but for the other diagram, it is triple line, right? Okay. Right. Okay. So then there's an example. I'm actually not going to work this one out. So there is a I already worked this one in the second year, so therefore you can quickly have a look on that one. But of course this is not needed. Just what I'm doing is here just to memorize the things, right? Okay. Right. So okay. Then there's another session we call first law of thermodynamics. Of course, not we have 4 laws of thermodynamics, right? I hope you remember this one, but I'm not going through this one, right? I'm going to stop the session for today. I mean, for this session. Then we will look on the Rankine cycle, right? Okay. So but you need the knowledge of this pure substance. Therefore I just quickly go to this slide. Then in the next session we can work on the Carnot-Rankine cycle and the Carnot-Webb cycle and the Rankine cycle. Okay.